Yesterday we learned about Michelson's rotating mirror experiment that was used to find the speed of light. We learned that it gave us a pretty good value for the speed of light, a pretty accurate value, certainly in the magnitude of 10 to the 8 meters per second. Let's spend a couple minutes just going over how that rotating mirror experiment worked and how we used it to find the speed of light. If we have two mountains 35 kilometers apart, or they don't have to be 35 kilometers apart, that's just the two mountains that Michelson used, 35 kilometers apart. Whatever the distance, doesn't really matter. We shine a flash of light from this Mount Wilson, that's the first hill, at this, looking at it from above, this mirror that has the potential to rotate. Right now it's not rotating. Right now it's just at rest, and you've got 8 sides of the mirror that are just plain flat, one spot, there they are. What you get here is this flash of light that's coming from Mount Wilson, reflecting off of side 4, and then bouncing off of it at the right angle to come down here to this other mountain that's, well, in the case of Michelson's actual experiment, 35 kilometers away. Bounces off of Mount San Antonio, 35 kilometers away, bounces back, hits side 6, and then bounces back over here and gets observed by the observer. Good, we see it. Hasn't accomplished anything because this mirror is stationary right now. Let's start spinning the mirror. And when we start spinning the mirror, we still may get a beam of light that reflects off of side 4. But by the time this beam of light goes, let's erase this now just so we don't get confused by what happened before it reflected. If this beam of light reflects off of side 4, goes down to Mount San Antonio, comes back up, and the mirror is spinning in the meantime, then we have an issue. If the mirror is spinning in the meantime, side 6 that reflected the light over to the observer just a minute ago, still might reflect light, comes back up here, reflects light, but it comes off at an angle like this. Side 6 isn't in the right place to reflect light to the observer. During the time that it took the light to travel that 70-kilometer round-trip distance, the rotating set of mirrors rotated enough to put the reflecting angle out of whack so that it reflects somewhere else. But what do? Crank up the frequency. If the frequency was 100 hertz, it's not reflecting the light to the observer. Let's crank up the frequency to 200 hertz, 250, 350, and so on until we get light observed by the observer over here. How do we get light observed by the observer if it's just the right frequency? Well, because side 5, if we're rotating this at just the right frequency, side 5 has come in to take the place of side 6. In other words, during the time that it took the light to travel the 70-kilometer round-trip distance from here down to Mount San Antonio and then back again, during the time that it took the light to travel that distance, the mirror has made exactly 1/8 of a rotation on its axis. Now, if we turn the frequency of the mirror up even more, what happens? Well, it reflects off at the wrong angle and doesn't get observed anymore. So we had just this right frequency, let's say 600 hertz. The observer observed it, but then we turn it up to 650, the observer doesn't see it anymore. 700, 800, doesn't see it anymore. But at some point, we turn it up enough that, oh wait, now it's not side 5 that's rushed in to take the place of side 6, it's side 4 that's now taking the place of side 6. Gets observed again. Now the mirror has made 2/8 of a rotation instead of 1/8 of a rotation. The observer will observe the light if the mirror has made exactly 1/8 or 2/8 or 3/8 and so on of a rotation during the time that it takes the light to travel from here to Mount San Antonio and back again. Now, how do we know exactly how many rotations it's made, 1/8 or 2/8 or 3/8? Start with a mirror at rest. Start with a mirror just sitting there like we did at the beginning of this lesson. Then turn on the mirror. Start rotating the mirror. You're going to see the light disappearing. As we turn up the frequency of the mirror, at some point you're going to see the light reappear. The point where you see it reappear, stop. Don't turn up the frequency anymore. You nailed it. You got the frequency at the right rate so that the light will reflect off of side 5 and get observed by the observer. In other words, if you turn up the frequency and you stop turning it up when the mirror has made 1/8 of a rotation during that 70-kilometer round trip distance, then you've got, you know that it's 1/8 as opposed to 2/8 or 3/8. If you keep turning it up, all bets are off, right? Then it could be 2/8, it could be 3/8, it could be 4/8, whatever. But if you stop turning it up, the first time you observe the light, you know it's made 1/8 of a rotation during that time. Okay, what's the method that we use to find the speed of light now that we've got the fact that it's 1/8 of rotation and the round trip distance here? Well, we know that we have to always write down the same two equations. Always, no exceptions. V equals d over t, and t is equal to 1 over f. What does this t stand for right here? This little t. Well, it's time, yeah, but specifically it's time for, sorry? It's in seconds, yeah. But the time for what, though? It's the time that it took the light to go from the rotating mirror to Mount San Antonio and back again. It's the time for 1/8 of a rotation. Versus this time over here, this big T, which is the period, which is the time for one complete rotation. Remember what we said yesterday? You're going to solve for one of these times, either big T or little t. Remember what we also said yesterday? The one you get is the one you don't want. So if you get little t, then multiply by 8 to get big T. If you get big T, then let's multiply it by 8. Sorry, divide by 8 to get little t. And then do your thing. Hey, this is... I love it when we get to this topic, because as much as the experiment itself might be a little bit hard to grasp at first, once we get it, it's just a matter of doing the same thing every time we do a question. We don't have to think about this, really. We just write down these two equations, and we just sub in numbers. We get one of the t's, and then either multiply or divide it by 8, and then we end up getting exactly what we're looking for. I say that I love these questions because of that. I like questions where we have to think hard, but it's nice to have a break every once in a while. It's nice to have a question every once in a while where we don't really have to think hard, where we can just follow a recipe and do it. Okay? And this is that question where we can follow the recipe and do it. All right, we had 3 questions for homework on this. I'd like to take a look at those 3 questions now on page 650. You want to do one of those, 2 of those? Number 2, okay. Number 2 says light reflects from an 8-sided set of rotating mirrors, travels 15 kilometers and back. All right, we got to be careful here, right? 15 kilometers is not the distance that Michelson used in his experiment. We're used to saying 35. This is 15. So the return distance won't be 70. The return distance will be 30. We want to know the frequency of the rotating mirror if it's made 1/8 of a rotation. Well, we know that we've got to write down my 2 equations. V equals d over t, and t is equal to 1 over f. Remember that little t is 1/8 of a rotation. Big T is time for one complete rotation. Question number 1 has a 12-sided mirror. So if we find little t in question number 1, what's it giving us? Not the time for 1/8 of rotation, time for 1/12 of rotation. If we have to multiply something, it's not going to be multiplied by 8, it's going to be multiplied by 12. If we have to divide, it's going to be divide by 12 instead of divide by 8. All right, let's plug in our numbers to see what we got here. Remember we said yesterday that if you're looking for frequency, you need to know a speed. We have to go with the accepted value for the speed of light since it's not given to us in the question. So that's 3 times 10 to the 8 meters per second. The distance that it travels is 30,000 meters. And my time is, well, whatever it is. 30,000 divided by 3 times 10 to the 8. 3 times 10 to the 4 divided by 3 times 10 to the 8. That's going to be 1.0 times 10 to the negative 4 seconds, I believe. Anybody get that? What do you do with that? Because it's not the time you want. It's never the time you want. The one you get is never the one you want. Times it by 8. If you got little t, how do you remember whether you times it by 8 or divide by 8? Well, you can logically think, right? You get a bigger time, you're going to times it by 8. But you can also have a little mnemonic device as well. You got a little letter, little t. You want big T. How do you get a big thing from a little thing? You multiply it. Okay? So to go from little t to big T, you multiply by 8 or 12 or whatever the case may be. You go from big T to little t, you divide. So let's multiply this by 8. That gives me big T is 8 times 10 to the negative 4 seconds. Now let's sub this in over here. 8 times 10 to the negative 4 equals 1 over f. F ends up being equal to 1 over 8 times 10 to the negative 4. Now, 1 divided by 8, I believe, is 1.25 times 10 to the negative, no, I want to say 3. Is it 1.25 times 10 to the 3? Hertz. Is that okay? Generally, these questions give you frequencies somewhere in the range of 5, 6, 7, 800 hertz, in the hundreds of hertz, not the thousands of hertz. Generally, they do. Can anybody just give me a real quick, brief explanation as to why this one was a little bit different? Why this one gave me 1,000 hertz or 1,250 hertz instead of in that normal range that we see of 600, 700 hertz? It's an 8-sided mirror, but our distance is quite a bit different than what Michelson used, right? If our distances are typical, 35 kilometers, 30 kilometers, and we have an 8-sided mirror, then we're going to end up with 600, 700 hertz, 10 to the 2. But if we use a 12-sided mirror or 15 kilometers, then all bets are off as to what you should expect to get for frequency. Okay? Okay, your homework over the weekend is the worksheet that goes along with this. And I can't remember the number. It's, I want to say 14 or something like that. You'll see what it is. It's the first one. It's the first one in the new unit. Okay. Actually, no, I believe it's the second one in the new unit, actually. It's titled Michelson. You'll see it. And it's in the worksheets that I've posted to Google Classroom. Okay.